Hello everyone, good morning. We can start lecture 14. So these are the topics for today's talk. Random variables. We continue with the random variable. Last time we only introduced this, but we did not go into detail. Then we will talk about something called expectation. And then we will see something called Petersburg paradox. And then we would like to see some spatial distributions. Okay, so random variable is something I defined in the last class, and here I will define independent random variables. So we consider two random variables independent if we have the following. Okay, so two random variables are independent if we have this. Remember that some comma sometimes is written for intersection. Okay, so sometimes we write intersection A intersection B as A comma B. Okay, so we use a comma in the sense that it's an and. Okay, so here x equals to x corresponds to an event, and y equals to y also corresponds to an event. We saw these notations in the last class, and if I put a comma, then it means event x equals to x intersected with event y equals to y, and that is equal to probability of the event x equals to x times probability of the event y equals to y. So this is the same independence that we saw before, but it's just that we are using a new notation here. Okay, and that should hold for all x and y. In other words, that should hold for all events. All the possible values of x and y that you're going to take. Hello, please mute your microphone. Hello. Okay. So then we call this these random variables independent. Okay. Then we say that the random variables themselves are independent. And that's why it's like it should be for all possible x and y. Okay. So whatever the events that correspond to x and whatever the event that corresponds to y, okay, they are independent as a whole. As a random variable, they are independent only if any event that they describe, that is independent. Okay. So in general, if two random variables are independent, then we also know we can also write like this. Okay, so for any set A and B, okay, so we can also say that for any set A and B, if x lies in some set A and y and x lies in some set B, then we must have that probability that x belongs to A and probability that y belongs to B. So this can be generalized for any two sets A and B. And this is something we also know from the previous description, that probability of A given B is probability of A only. So the occurrence of B doesn't change the probability of A, has no influence on the probability of A. So that's just written in terms of random variable. Let us see some problems on independent random variables. So we toss a coin twice. Let x denote the number of heads we observe. After this, we then toss the coin two more times and define y to be the number of heads we observe. So we toss a coin first, and that is tracked by the random variable x. And furthermore, we toss two more coins, and that is tracked by the random variable y. Okay. So we see, in this case, these are like these two random variables will be independent. Okay. So occurrence of x has no influence on the occurrence of y. Okay. So what is probability of x less than 2 and y greater than 1? Okay, so what were the y number of heads we observe, and x was also the number of heads we observe. Okay, so both are counting the number of heads, but x is counting the head only for the first toss. So this is the x, and then y is counting the heads for the next two tosses. Okay, so two more times is tossed. So and we have to compute the probability that x is less than 2 and y is greater than 1. Okay, so let us compute these. So we know that x and y are independent because probability of x happening has no influence on what is the outcome going to be for the next two tosses. So that's where independence will be used to compute this probability. So solution to this will be, so we want to compute probability that x is less than 2 and y is greater than 1. Okay, so this is the probability we want to compute, and we use the independence because this is independent. So this will be probability of x less than 2 times probability of y greater than 1. Okay, so this is because x and y are independent. Okay, independent. Okay, so that's why we could write this as a product. Now probability of x less than 2 is the same as like probability of x0 plus probability that x is 1. Okay, so that we can write like this. Okay, so and then probability that y greater than 2. So probability that y greater than 2, and so y greater than 1 we are asking for, and we already know that y cannot be more than 2, because if you are doing for the next two twine courses, the maximum heads you can get are 2. Okay, so y is less than equal to 2, but y is greater than 1, so this implies y is equal to 2. Okay, so if that is the case, then this is probability of so PMF, right? So and y is equal to 2. So this is what we have. So now we know that we can compute this, the probability that x equals 0. So what is the probability that okay, so I think we are missing something here, right? Because we tossed a coin twice. So actually for x also we have like 2, right? Because we toss a coin twice. So x is like 2 possibilities here. So we toss a coin twice and let x denote the number of head we observe. After this, we toss the coin 2 more times. Okay, so this is like this form. Okay, so up to here. Okay, so so for x, this is the thing. So what is the probability that x will be 0? So what is the probability that you will get a 0 head? Okay, so here for x, the possibilities could have been like 4 possibilities could have been there. So either would have been head or head tail, or tail head, or head tail. Okay, so for x, these were the possibilities we had, and out of this we are asking for what is the possibility that there were 0 head. So 0 head is the case when we have tail. So this is like 1/4. Okay, and probability that it's just 1 head, right? So so it's like exactly equal to 1 head, right? So exactly equal to 1 is this case. This is exactly equal 1 head, right? So so this is like 2/4. So this is like half. Okay, so that's the, and then what is the probability that so for y also actually we have the same case. Okay, so same for y, same. Okay, so for y also same, and we are asking for heads, right? So 2 heads. So if 2 heads, then it is 1/4. Okay, so it's like 1/4. Okay, so this is like 3/16. Okay, this is 3/16. So that's the answer. So we have, in this case, what we saw in this example is that we could use the fact that 2 random variables were independent. Okay, the fact that x happened had no influence. We know that. Okay, so that's like given thing. We know that there is no influence of x happening on y. So these random variables were independent. Okay, so now what I'm going to define is something called expectation. So expectation you can think of as something called like average or mean. So mean you may have seen before, maybe in probabilities or in a little bit of statistics that you have done. So these are statistical terms, okay? So mean and average or whatever, like the mean and average are like the same thing, and variance and so on. So we are touching a bit of statistics already, right? So let us see what is expectation. So expectation of a discrete random variable x is defined as this, okay? So given a random variable x, this is how you are going to compute the expectation, okay? So so expectation of x is some random variable there, and then what are the possible values that x is going to take, right? So x, let us say the possible values for x are x1, x2, dot dot dot, let us say xk. It could be like infinity as well. So to compute this, what you also need is a PMF, okay? So this is the PMF. So what you need as a first step is PMF, okay? PMF of the random variable x, okay, to compute the expectation. And another thing you need are the actual values of x, values that is going to take, and then you sum over those values of x, okay? So in this example, I will sum over I equal 1 to k, and then xi, and then PMF of xi. Okay, so PMF describes these probability values for xi. So that will give me the expectance. Okay, if k goes to infinity, then you put k infinity here. Okay, and if it converges, then you have seen real analysis a little bit, then you know when infinite series might converge or diverge and so on. Okay, we'll come back to this a bit later. So the definition of expectance is clear. Obviously, it makes sense only when PMF is greater than 0. Okay, because PMF is equal to first of all, it's a probability. So PMF of x will always be greater than like equal to 0. So that's given. And whenever PMF of x is equal to 0, so that those cases don't contribute in the sum. Okay, so those cases we have to neglect anyway. Okay, so this is the most important thing that you should remember. Expectation of x is PMF of x times x. So note we sum over all the values of it, there's no zero probability, and the other names of expectations are mean. So mean is something you may have seen in statistics chapters in 11th or 12th. So then it's also called expected value. Sometimes it's called weighted average, because it's like you do some kind of weight and so on, weighted average. I mean the weights are like this, okay? And then center of mass, you can think of this, and you can also think of this as a first moment. This is a better way to remember this as a first moment, because there are also, as you can guess already, there could be second moment, third moment, and so on. So we will define more generally what moments are after some moments, but this is I would like to see these as moments, okay? First moment, second moment, third moment, so on. So okay, so let us see some example of expectation. What is the expected value of a six-sided die roll? Okay, so how do you go about this? So the steps that are involved are what? So I need a PMF, right? So what is the PMF of a random variable? So what is the random variable here? Okay, so what is the random variable for us here, right? So random variable is like the outcomes here, right? So it's like 1, 2, 3, 4, 5, 6, like the typical like random variable that we are thinking of default. Okay, so what is the random variable here? Yeah, this, and then the second would be like the PMF of x. So PMF of x is how much, right? So PMF of x is so getting, so what is the probability of getting a 1? It's like 1/6, and this is true for all x. So for all x in 1, 2, 3 up to 6. Okay, and it is 0 otherwise. Okay, it's 0 otherwise. So that's the PMF, and that's it. So now we can compute the expected outcome as a number, right? So as a number we are saying, so expected on average, what is the number that you are supposed to see on average? That's what he's trying to say. Okay, so on average, right? So this is like so this is I equal 1 to k. So k here in this case is 6. Okay, and we have xk and pmf over xk. So this is like 1 times, and then pmf of 1 is 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 plus 6 times 1 over 6. Okay, so what is the the value that you get? So if we calculate this, what do we get, right? So so it's like in the denominator we have 6, and then you have like what, 1 2 3 4, so 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, so how much, right? So it's 3 6 10 15 and 15 and 6, right? So 15 and 6 is how much? Okay, so 15 and 6 is 21, right? So and divided by 6. Okay, so this is how much? So 3 7 3 2 and 3.5, right? So and that is kind of expected, right? So you're getting a number somewhere in between, somewhere in between, right? So it's 3.5. So on average, if I throw a die, on average the number that I'm going to get is 3.5. But 3.5 is not any of these this possible output. But when you're talking about average, it may be a number that's not there in the outcomes, right? So we are talking about average. So on average, we will find we expect to get 3.5 as an output. Okay, so that's how we compute the expected outcome. So this is the solved example here. Okay, so now I will I would like to derive some properties of expectation, and it turns out that expectation is a linear function. So I would like to recall linearity. Okay, what are linear functions? So let A and B be two vector spaces. In general, like the way you understand this, a function f from A to B is called linear function if the following holds: f of u plus v is fu plus fv, where u and v are vectors. Okay, so u v in A, and f of c times u is c times f of u, where c is a scalar. Okay, so I guess you remember this these two conditions for linearity. And then equivalent definition for this could be like I combine these two to get this equivalent definition, where f of alpha u plus beta, it should be beta v here. F of alpha u plus beta v is alpha f of u plus beta f of v, where u and v are the vectors in the domain. So A and B are vector spaces. So that's why vectors addition makes sense in a vector space. In general, we may not be able to add things, but to be safe, we say it's vector space. So we can add, we can also do scalar multiplication in vector space, and after scalar multiplication, it's guaranteed that CU is also in A and U plus V is also in A. That is why we need a vector space. Okay, because vector space preserves this addition and scalar multiplication. So this is something we recall from linear algebra, let us say, and then now let us say this. So which of the following functions are linear? F of x is x. So is this a linear function? Okay, so tell me in chat, what do you think? Is this a linear function? So tell me, is this a linear function? Okay, so you try to reply. Okay, so what the chat is like hanging somehow. I don't know why. Okay, anyway, so this turns out to be a linear function, and then is this a linear function? The second option. What do you think? Is the second option a linear function? Okay. So chat will never open. That's so. Let me continue. So you can check that this is a linear function. Linear function. This is a not linear function. This is not linear. This is not linear. This is not linear. This is linear. This is not linear, and this is linear. Okay. So you try to verify this. Okay, so the linearity, I have given you the definition of a linear function, and you have done linear algebra. So by now you should be an expert in knowing what is a linear function right now. Okay, so now I can move ahead and describe this. So what it is trying to say is expectation. Expectation is a linear function. So expectation is what, right? So expectation goes from the space of like random variables, right? So it's the space of random variables, and it goes to some real number. Okay, so expectation is some number, right? So it goes. The domain is the set of random variables. So this is some random variable. Okay, ax plus b is some random variable, because I can add constant to a random variable. It doesn't matter. Then it says it's like a times expectation of x plus b. Okay, so let x equals to 6 be a 6-sided dice roll. Then let y is equal to 2x minus 1. Okay, so what we are trying to get from here is like quite interesting things. Like now I'm able to define some other random variable based on x. Okay, some other random variable which is 2x minus 1. And then if the expectation of x is given to me, then due to linearity, expectation of y could be found, because expectation of y will be expectation of 2x minus 1. But since expectation is linear, e can go inside and scalar can come out. So this is like this. Okay. And what is the expectation of a constant? So what is the expectation of a constant, right? So right now I'm here, right? What is the expectation of a constant? That's very interesting, right? What do you think will be the expectation of a constant? Can you tell me in the chat? Expectation of a constant. So anyone, what is expectation of a constant? Like or expectation of a 1? Yeah, the constant itself. Thanks, Akash. Okay, so it will be the constant itself. Okay, because if you see the expectation definition, right? So expectation of a constant, and you will sum over whatever PMF values you are supposed to take. Okay, I equal 1 to whatever, and then you have this PMF of xk, and then you have this c and so on. So the constant comes out, but this guy becomes 1, right? Because it's a PMF, so PMF sums to 1. So expectation of a constant will remain a constant. Okay, so this will be 2 times expectation of x. Sorry, so it should be capital X, because expectation is always on the random variable, not on the not on like small x. Okay, so this is like 1. So this is 2 times 3.5 minus 1. Okay, so this is like 7 minus 1 is 6. Okay, so that's how, due to linearity, we can compute expectation of some other derived random variable. Okay. And then another property is like expectation of x plus y is expectation of x plus expectation of y. Okay, so this again follows from the linearity. Linearity property. All this is something we can prove. Okay, that's what I'm trying to say. Proof from the basic definition. Okay, so use the definition of xi pxi. Okay, just by using this definition, you can prove all these results. Okay, so let us see some example of this. So consider two dice rolls. X is the roll of the first dice, and Y is the roll of the second dice. So, or die. The die is like the singular, right? So die. So here it's the dice, and here it's the like die, right? So X is the roll of first die, and Y is the roll of second die. Then expectation of X plus Y is what? So we will use this, right? So expectation of X plus Y will be expectation of X plus expectation of Y, and and what is that, right? So roll of the die 1, and then we have roll of die 1, and then we have roll of die 2. Okay, so expectation of the die 1, we know we have calculated before, is 3.5, and then y is also 3.5. So the sum will be 7. Okay, so that's the answer. Okay, so and then let us say expectation of a function of a random variable. So that's now more generalized. Okay, so how do you find the expectation of g of x, where x is the random variable? Okay, so more generic formula is this: expectation of a function of a random variable. Okay, expectation of, so this becomes a special case of this, because this is a special case, because I could have it's also trying to predict the you can say it's also trying to tell us the linearity and so on, but this is a special case because g of x could have been taken as ax plus b. Okay, so so this is defined to be this g of x, and then p of x. The g of x is just the function value. Okay, it's not the PMF you're thinking of. Okay, this is the PMF of the random variable x, and this is just the function that we have. So we will evaluate that for x. Okay, if you see this example here, then so x is the six-sided die. Okay, so let x be the six-sided die roll, and then g of x is x square. If expectation of x is 3.5, then what is expectation of g of x? So to compute this g of x, what will you do, right? So to compute g of x, we will invoke this formula, right? So this will be sum over I equal 1 to, so we know that there are like 6 outcomes. Okay, and then g of xi, and then p of xi. Okay, now as I said, this is the function evaluation. So g of so g for us is x square function, right? So this is like nothing but xi square, and then this is p of xi, right? This is the sum over I equal to 1 to 6. So now you put the values here. Okay, so x1 was 1, right? So 1 square times PMF of getting the output 1 was 1 over 6 plus 2 square 1 over 6 plus dot 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 plus 6 square 1 over 6. Okay, so this will be the expectation of g of x. Okay, and you compute these values. I'm not going to like compute this explicitly. So in general, you see it's very in general you can compute expectation of some function of x, arbitrary function of x actually. Okay, because only thing you need is the PMF of x. As long as PMF of x is given to you, function evaluation is an easy thing, provided that the function is defined for those values. Okay, then it's an easy thing, right? What if I would have defined g of x to be like 1 by 1 minus like x or something, right? So at 1, like it's not defined, right? So at 1 it's not defined. So okay, So we can compute expectation of a function of a random variable using these formulas. So proof of linearity of this. So proof of linearity follows from the definition itself, right? So for example, expectation of E of ax plus b is what, right? So we know that. So this will be nothing but the sum of ax plus b and then px. Okay, and this is the sum over x we are doing, and this is nothing but ax px plus b px, this is sum over x, and this is we can, so linearity is exploited here now, right, inside, because these are some numbers right now. So this is like x px sum over x plus b px. Okay, so sum over px, this boils down to 1. So this is a e of x plus b times 1. Okay, so that's the proof of this. And now if we try to prove we can also try to prove the second one. Okay, so we may try to prove the, okay, so you try to do this also, okay, as an assignment, why this should be true. Okay, so I will put this as an assignment. Okay, let's see. Let us do some more problems on expectation. So let us see this. Let x be a discrete random variable whose PMF is given as follows. Okay, so that's like some outcomes are there and probabilities for those are given to us, and otherwise it's 0. Now we are given, let us say, a random variable which is absolute value of x. Okay, so absolute value of x is given to us. So what will be the expectation of y, right? So again, like we go by the formula, right? So expectation of y is like a g of x for us, right? So y is the sum over g of x and then p of x. Okay, and these are the all possible values of x. I just write x. So this means that I will roll over all the possibilities of x. Okay, so if we do this, then yeah, so we can get the answer for this, right? So if we substitute the values of x, so first one is like g of -1 and then p of -1 plus g of 0 p of 0 plus g of 1 p of 1. Okay, so g of -1 is the absolute value of 1, which is 1, and p probability p of -1 outcome is 1 over 3. Plus g of 0 is 0. Okay, so that goes 0, so I don't even have to compute other, because absolute value of 0 is 0, and this is 1 times 1 over 3. Okay, so overall, what is this? This is 2 over 3. Okay, so expectation of y is 2 over 3. Okay, so that's another example of. Now let us see what role expectation has to play. Let us say if you are playing in some game, okay, and these games could be sometimes not intuitive, just like Monty Hall. You can think of this as Monty Hall of the expectation problem. Okay, it will actually, this is even more tricky than Monty Hall, because this one leads you to paradox. Okay, so let's see. So consider a game, but before that, I will introduce you to. Well, this is something I have already done actually. So okay, so I can just write down. So consider a game where die is roll. After the roll, the total money. So I have made this die roll problem into a game actually. So let us say someone rolls a die, and then after the roll, the total money that you get is the output from the die. Okay, so someone rolls a die, and you get a 6. You take 6 rupees. Okay, if you are unlucky, then you get 1, and then you get 1 rupees. Okay. So the question is, how much money would you like to pay to enter this game, or to play this game, right? So what you know as an expectation is like, on average, it is expected that the outcome you will get is 3.5. Okay, so it makes a little bit of sense that you would not like to invest more than 3.5 in this game, because on average you are going to get 3.5 only. Okay, not maybe like if you're lucky, as I said, you can get 6 also, but on average it's 3.5 rupees that you get as a return. So maybe your investment initial would be less than 3.5. Okay, it depends on your judgment, like how much you want to gain or so on. So you can do some expectation calculation to see how much is safe. Okay, given that this is a random experiment. So in this case, you know that maybe you would like to pay 1 or 2 rupees to be safe. Okay. So in a more, so we can start with some other more tricky problems. Okay, so let us see a game. So consider a fair coin. We toss the coin, and if it is heads, the game ends. Okay, if it is heads the first time, the game ends and you win 2 rupees. Okay. If it turns out to be tails, then I will toss it again. Okay, so I will toss it again, like the game doesn't end. Okay, the game ends when the head comes, and then, so in this case, in the first case, you got 2 rupees. Okay, so let's see, like, what are the rules? If it comes out to be tail, I will toss it again actually. Okay, and if it is heads on the second toss, you win 4 now. So it's like double, right? So it's 4 now. If not, if there was no head, then I will toss it again for you. And then if I get indeed a head again in the third toss, then I give you 8 rupees. Okay, so it's like again double of the previous. So in general, if the first head appears at the nth toss, the first head appears at the nth toss, then I have to give you 2 to the n rupees. Okay, so that's the game. So now there is an entrance fee to play this game. Okay, there is entrance fee to pay this game. What is the maximum amount of money that you will agree to play this game? Okay, so in the previous example of the die, you saw that the expectation was 3.5. So maybe you would say that investing 1 or 2 rupees is kind of okay, because on average you expect 3.5 rupees in return. On average, we are saying, right? Not always, but on average. That's how you play a game, right? So you calculate some estimate. So here, this is another game. Okay, so you will get, if you get head in the first time, actually you are least lucky, because you only get back 2 rupees, right? But if the head doesn't come, and if the head comes in the second time, then you get 4. If head comes in the third one, then you get 8 rupees and so on. So it seems like it's good for you when there are lots of tails, and then a head comes after a long time. Okay, let us say nth, after n minus 1th trial, you get the head at the nth, and hence you get away with 2 to the n rupees. Okay, so that seems to be a good thing, right? But so this is the rules of the game. These are the rules of the game. Now the question is how much money you would pay as an entrance fee to play this game. Okay, what is the sensible way to invest a money in this type of game? Okay, so you may say, so let us see the tabular data a little bit, and then you will get. Okay, so let's see. These are the outcomes that you have. Okay, so if it's the first trial, okay, the price that you get is the 2, and the probability of that happening is half. And what you get back, if it indeed is a head in the first toss, then you get 2 rupees done. If it was not head, then it will move to the second trial, and price here is 4. The probability of that happening is 1/4. Okay, but you get 4 rupees back. Okay, so what does your intuition say when you look at this tabular data? Let us say you want to play this game and you made this table. Okay, and you know how to compute the probability, so you also computed the probability, right? So when you look at this, then you will say that, oh well, although I might get more and more, but the probability of those happening are rather less, right? So if I invest, let us say 100 rupees, then the probability of making a profit, or in other words, probability that I will get 128 is 1 over 128. It's 1 over 128 probability that I will get I will get up to the 7th trial, and that will give me 128 rupees, and then I will make a 28 rupees profit, right? Because I invested 100, let us say. Okay. So according to this, if you see, like, you are playing with a game, you are playing a little bit with your chance also, because you, like, you don't know, like, who knows, like, you have, like, who knows that you may have invested 100, but the game went up to, let us say, the 10th trial. Okay, so you are getting 2 to the 10, okay, which is way beyond 100. So although you invested 100, the return you are getting is lot more. Okay. But the chances of getting up to 10 is also way less. Okay, so it's like 1 over 2 to the 10 is your chance of getting up to that stage, that trial. Okay, so these are the problems you have in this. Okay, so what do you do in such problems, right? Obviously, like, one may say that I invest only 1 rupees as a minimum, but this is something not you decide, right? It's like this is the game I am opening for you. So this is the game I am opening for you, and I decide the minimum threshold. Now you will take a decision. So these problems are like goes into decision theory. Okay, so there is a lot of things written about this problem in decision theory. Okay, but let us say that I have opened this game, and then I have set a minimum. Let us say I have set a minimum entry fee of ₹5. Now you, as a customer, have to decide whether this is worth investing 5. Okay, it is whether you will play this game at all, given that the entry fee is 5. Now you have to do some calculations based on this, like you have invested 5. What is the expected outcome you're going to get? Okay, so so let us make some usual observation that I have just told you right now. It's just a recap of that. For those who cannot watch video, they can go through the slides, right? So if we pay ₹1, then if the game ends in the first toss, then we get 2 rupees. So if I pay ₹1 and game ends in the first toss, then I get 2 rupees. So the gain profit I make is 1 rupees. Okay, so if we pay say ₹10, and the game ends in the third toss. So if I pay ₹10 and the game ends in the third toss, then I only get back with 8 rupees. So I lose ₹2. Okay. So naturally at this stage, we wonder what is the expected value. Now, if I calculate the expected expectance of the random variable, this is where you will see the paradox. So if I go by the expectance, so expectance will be like the 1 times the probability of is it 1? It should be 2, right? So the output is like 2. Utility, or what I'm going to get as a return, which is the price in this case. Okay, so it's the same as the price. So what I'm going to get as an output is 2, and what is the probability of that happening is 1 over 2. What is I'm going to get as a second output 4, and the probability of that happening is 1 over 4. And the third, I'm going to get 8, and the probability of that happening is 1 over 8. So if you compute this, then you get 1, 1, 1. So you get up to infinity. Okay. So technically speaking, the expectance, the expected outcome of playing this game is infinity. Okay, expected outcome of playing this game is infinity. So technically, what does this mean? Like, this means that, so are you willing to pay any amount to play this game, given that in theory you can win up to infinity? Okay, so in theory you will win up to infinity, right? So from the expectation calculation, I see that in theory I will get up to infinity. So that's an interesting thing. Like, the maths tells me that in theory I can put any, I should be giving any entry fee, right? So so can you see why this seems to be a paradox? Okay, so why this seems to be a paradox, right? So it's like we get infinity, and so it is paradoxical because of the following reason. Okay, the reasons are, like, in reality very few would pay even rupees 15 or even like less than 15 actually, because probability tells you something else, right? So if you get 15, right? So if I am paying 15, then it means that I must be able to go beyond, the game should go beyond fourth at least to start making profit, right? So here I will make a profit of 1. If the game goes, luckily, let us say if the game goes beyond let us say goes up to the 5th trial, then I'm making more profit, like 17 rupees profit I'm making, and so on. But the problem is that the chances of the game going beyond 5th, 6th is diminishing a lot actually. Although the utility, the price money also I am proportionally increasing, but the chances of this happening are rather low. So if you play this game in a realistic scenario, even with a simple common sense, you will say that is not making much sense to me. Okay, so this is why this is a paradox. Okay, so the math, the expectation tells you that that you should be willing to pay any amount, because expectation is high, it's like so high, like infinity. But in reality, you won't be paying this. You won't be willing to do so. Okay, there is a risk involved. So this is one of the very peculiar problem, and that's why it's called paradox. Like in reality, you may not have to depend. You may not have to depend, especially in economic scenario. You may not have to depend on expectations. So maximizing expectation is not always a good thing. Okay, because of conditions like this. Okay. So when you are into economics and so on, and if you go ahead and study like decision theory and so on, so it's not always viable to maximize your expectation. So in this case, your expectation is like maximized up to infinity, but it doesn't make sense to pay, I would say, even 5 rupees to pay to play this game, because your chances of making a profit is rather low. Okay, so that's why it's termed as a paradox. And but things would, and one of the reason why this turns out to be a paradox is because of the infinities involved here. Okay, the infinite number of times you are doing the sum, although it's going up to the probability of those happening are going less and less, but the fact that you're doing sum each time, you are getting one additional as an expected return. Okay. So from decision theory point of view, the way people argue this is like like for you getting additional one, when you are a billionaire, getting one additional is not worth. Okay, and moreover, this game cannot be played up to infinity in realistic scenario. So this game must have to stop at a finite time. Like each time you play a game, let us say it takes 1 minute, right? So so the return that you will get will cross more than your lifetime. Okay, if you really do this calculations and so on. I will put the link to this. Like even if you have numbers as wealth as big as Bill Gates and so on, you will see that to make profit you may have to run for 900 years and so on. Okay, so so in reality you have to think, okay, when you are making decisions. Okay, so so analyzing, so one more possibility could have been this, like we don't increase the utility beyond certain points. So we put a cap on let us say 32 rupees. So once it hits 32 rupees, regardless of the game you keep playing, each time I'm only giving you 32 rupees. Okay, I'm not giving you more than 32 rupees. I'm not increasing the utility. So the moment you do that, then the expectation that you calculate after this, remember, if you stop here, then you get 1, because it's like 2 times half. Okay, so that's the first, so you get 1. Okay, the second one is 2 times half plus 4 times 1 by 4. So this is again 1 plus 1. So each time you see 1 plus 1 plus 1 you are getting. But if you go it up to 32, and then after that After that, you will have 1 over 64, and the utility you are giving is only 32. Okay, so this becomes like half, 0.5. Okay, same way it will be 1/4. Okay, and so on. So then your utility, your expectation is now decreasing now. Okay, so from here onwards it will converge if you do the series, right? So this is like half plus 1/4 plus 1/8. So what is this, right? So where does this series converge, right? So you have done this in real analysis, right? So this will converge to some value, right? But like something, maybe it will be like something like 1 point something. Okay, I'm not sure about the sum of this series. Okay, I also have to do calculation, but maybe it will be something like 1 point something. Okay, maybe. Okay, so this is what it could be. So in this case, your expectation is not blowing up. In this case, it will end. Okay, so in this case also we will make some observations. So if I pay ₹1, I still get ₹2, so I get a profit of 1. If I pay ₹10 and the game ends in the 30-second toss, in the 30-second toss, then on average we get ₹6 and we lose ₹2. Okay, so that's what I'm trying to say, on average. So now if I add, so there are 5 ones, right? 1, 2, 3, 4, 5, and then plus remaining I claim to be 1 point something. Okay, I have not calculated the sum of this series, so it will be somewhere around 6 on average. So if I paid ₹10, okay, and even if the games goes up to 30-second toss, let us say, from 6 to 32nd, I'm hardly in the expectations, I'm hardly adding roughly 1 point something. Okay, so it's like 5 plus 1 point something, which is approximately 6. So I'm not going beyond 6 in expectation, right? So it is not worth paying 10 in this case. In this case, we may say like ₹2, I would bet like ₹2, 3, 4, something like that. And certainly you may not want to invest more than 6 in this case. Okay, so when things converge finite, then it makes sense what is to be done. But in general, you have to be a bit careful in deciding based on expectation. Okay, so these are the things, and yeah, so this is what I said. It's written here. Okay, so I may not be able to continue to the distribution. So next part is the distributions that we will do in the next class. So we will do a couple of distributions, like 6-7 distributions are there, and those are prominent in like day-to-day applications. So with this I will end. There will be a lot more problems. There will be a lot more problems in the tutorial, so you must do the tutorials to do a lot more problems. Classes are mostly for theories. I have to go rather quickly to cover a lot of ground. Okay, so thanks for your attention. Have a good day. Okay, bye. I had some problem with the chats. I was clicking on chat and it was not opening. I don't know why. So I could not interact much with you today, and this happened also last time. So I don't know why it's so much lagging. Okay, anyway, yeah, thanks, bye.
Hello, sir. Hello.